Yeah, let's move on with the splice design. I have worked on the splice design from the last 2 weeks. Um, so what are actually splices? So splice is a structural connection that joins two steel members end to end so that they can act as a continuous member. So when we have two different members, we can join using the splice plates, bolts, or welds. So basically a splice is a lap member that join ends to ends and transfer forces through high strength bolts, welds, and splice plates. So why is splicing actually needed? So the first thing is like the availability of the fabrication limits. We do not have everything accessibility at the site. Longer spans and complex shapes at the site. The design requirements as per the contractors, and even the load transfer and structural integrity that we involve while doing the design calculations. So at what locations the splicing should be done. So I was actually working on the A301 to A306. So as you can see in the graph below, so this is as you can see my cursors, this is the span length, and this is the moment that we got at this for this span length. So we finalized a location where the moment was actually um, like the moment was actually zero, like it was going from negative to positive, and we finalized like at what location the splicing should be done. So basically it is said that the splicing is done at the point of contraflexure, which is the inflection point where the moment is zero. So because the placement of the splices near the point of contraflexure is advantageous because of the lower bending moments, and we need to only basically design for the shear forces. So, however, these slices are both designed for the shear and the bending moment, which I'll be discussing further. Let's move on with the stress distribution diagram for the I section. So as you can see over here, the first one is the bending stress distribution. So here, as you can see, like the majority of the stress due to bending moment is concentrated at the tip of the beam, that is the flange, to make sure that the all moment is transferred from one beam to the other. So the flanges are connected. So the flanges are said to be the um, like it is said to carry all the bending stresses, all the moments. And as you can see in this shear stress distribution diagram, like the majority of these shear stress is at the web location. So the web splices are taken to withstand the shear forces. So like the web is for the to take into account the shear stresses, and the flanges are taken into account to withstand the moment. So this is the basic, the small sketch of uh, the sketch for the splice design. So this is the elevation view for the splices. So this is the flange splice plate, the flange splice plate, bottom flange splice plate. This is the web splice plate. Yeah, this is the same. And this is the top layout of the flange splice plate, and this is the web splice plate. And these are the bolt layout, like how they are laid out at the site. So there are various load cases used as per the ASHTO 3.4.1. So sorry. So these are the load combinations used for our design of the splices for the A301 to A306. So the first one is the DC1, which is the non-composite dead load. So which actually represents the self weight of the structural components that the bridge or the steel work is bridge or the steel work before it is casted. And these are basically the steel girders, stiffeners, cross frames, splice plates, and diaphragms. And the second one is the superimposed composite dead load, that is DC2. So this basically represents the superimposed dead load that the structural system is in place, like when it is after casted. So these can basically represent the parapets, barriers, sidewalks. And if we have like the third one is the future wearing course of this wearing course, like if we have some wearing course like some asphalt members or some wearing on the top of the deck, so we use so we add the sorry we add the dead load for the wearing course as well. So since we are not using in this, so we just assumed just took it as zero. And we also have the live load impact, like the live load producing positive and the negative bending moment, plus the additional effect due to the vehicle dynamic load is also taken into considerations for the calculation of the splice design. So what are the different kinds of load combinations used for the splice design? So the first one is the strength one. So these are all taken from the ASTO LRFD. ASTO LRFD. So the strength one basically involves the combination relating to the normal vehicular use of the bridges without the wind loads into consideration. And the second one is the service two, which controls the steel structure for slip critical connection. So basically, we are using the bolts for joining the steel members. So service to load combination plays a major role in the design of the splice design. So actually, how is it functioned is like flanges carry bending moment. So like most of the tension and the compression forces, like if we have a tension at the top of the flange, we have the compression at the bottom of the flange, so it goes on vice versa. So at ultimate loads, the splice place, like it should not fail in the ultimate loads. So ultimate loads basically represents the strength one. So we check the bolt shear, net section rupture, block shear, and the splice plate capacity against the strength one forces. And as per the ASTO, which requires the flange splices to be slip critical, so we design it against the service two forces as well, to so that it is slip critical. And the second one is the web. That's the shear component that carries majority of the shear force, as we have seen in the stress distribution diagram. The bolt and the plate capacities in the shear are already checked are already checked in the strength one. So basically, we design the web plates for web splice plates for the service to load combination. That is the slip critical combination. So these are the load combinations that we have used for the flange splice plates and the web splice plates. So as you can see here, we have used the strength one and service two, and for the web splice plates, we have used the service two load combination. So what are the basic design checks for the splice design? So for moving on with the flange splice design check, so we check for the bolt factor and shear resistance. These are all taken from the different clauses from the ASTO LRFD. So the bolt shear strength should be greater than the applied shear demand for the applied shear demand that we have, and the bolt nominal slip resistance as per the service to load combinations, which checks slip resistance under the service to load combinations and prevents relative movement between the flange and the splice plates. And strength limit state design, so ultimate strength check for the connection, which ensures that bolts and plates don't fail under the ultimate factored ultimate loads. And we have the slip resistance design. So for the bolt and plate geometric layout, for the transverse gauge, for the longitudinal gauge, or for the diagonal edges of the bolts. And moment resistance check for the strength one, like the positive and the negative, that the flange splice plates must resist the bending moment transferred through the flange. Uh, uh, um, because the flange plates are more critical for tension and compression. And the splice plates, like the for the splice plates, we check it for the factored yield resistance for at the tension net section or to the gross section check, net section fracture resistance for in the tension, block shear rupture, as you can see in the figure over here. So block shear rupture actually, it is a kind of failure where the connection it tears apart due to the combination of the tension and shear stresses, which acts perpendicular to the plane of the material. So these kind of failures, so we need to take into account the block shear rupture for the design of the splice design. and slip critical check for the service to service to, like it should be like the service to load combinations we have used. And similarly for the web splice design, we check for the bolt factor and the shear resistance, bolt nominal slip resistance, strength limit state design, slip resistance design, which we have already previously discussed in the flange splice plates, bolt and geometric plane layout, how the play bolts and the bolt and the plate should be means the layout of the bolt should be done, and the layout check, the splice plates, factor shear yielding resistance, the rupture resistance, and finally the bearing resistance, like the bolt presses, the presses against the edges of the hole, and which kinds of tears apart the plates and cause the failure. So we need to check for those as well. So these are the design considerations for these splice plates. Yeah, that's it. Any questions?
Okay. Yeah, that's good. A good presentation. Yeah, good preparation for that. Yeah, my question is splice
Yes.
design we should do for the moment and share at the section, or for the capacity of the members, capacity of the flange and capacity of the web. So these splices should be designed for the capacity of the flange and web, or just for the moment and shear at that section.
So flanges should be designed for the capacity, like the capacity of, for example, we have the girders for like the section of W30 by 173. So that girders have particular capacity. So based on that, we get the moment and the shear
Moment, yeah.
at that particular location.
Your
So
location, yeah. So
yeah,
we don't design for the moment and shear at that location. We design for the capacity,
capacity.
right? Okay, that is what my feeling is. Right, yeah. But I forgot other things, yeah. But yeah, those, that is, I think. Hmm. Okay, good.
Ayush,
Actually, it should. Yeah, yeah, yeah.
uh, yeah, go ahead. You're
Okay.
telling something. Go ahead.
Yeah, like the plan, like the splice plates, we where like the locations are where we put these splice plates.
Yeah, we
So
play.
we
Yeah,
take
look,
into
yeah, we.
yeah,
Yeah,
we
go
take
ahead,
into
go ahead, please.
we take into considerations like what are the shear stresses and the moments at that particular location. So we design it for that moment and the shear stresses. So as we can see, like these are the different moments and the shears we have taken into considerations.
You are saying not for the capacity?
Like the moment and the shear depends upon the capacity of the section, like what moment and shear we can get at that particular location.
Yeah, you can, somebody can look
I
in
Yes.
the design manual. So yeah, I think splicer should be designed for the capacity of the for the members, for
I,
they are transferring that moment transfer, right?
I
So
Yes.
mm,
There are
yeah.
some manuals which do require that. Abhishek, I'm just muting you because I'm. So Ayush, the question from Mansoor was that the splice plates that you are designing it for the moments and shear you are getting from the superstructure, right?
Yeah.
So he is saying that there are some design manuals which require you to like design it for the moment and shear which you're getting for superstructure,
Hmm.
but also like somewhat match the capacity of the girder that you have, the
Okay.
flange plates of the girder that you have.
Oh, okay.
So I have seen this clause at places as well, but I'm not sure if I can actually recall it from Ashta exactly. But that is something that we should look into it. Like Ayush, you can look into
Correct. Yeah.
Yeah,
this thing and also include that in your presentation if you see that.
yeah,
That was
sure.
a good point here.
Good. Okay.
Yeah, it depends. So if you follow AISC purely, they don't require like full capacity achieve. We don't need to achieve the full capacity from the splice plates, but ASTO requires you to achieve the full capacity of the member for the splices. Uh, And other, if you're doing buildings versus roadways, your stipulations change. But yeah, we do for the full capacity. The spreadsheet that you're using is an NSPS spreadsheet,
Hmm.
which follows mostly the AIS requirements.
Hmm.
And if you go to the beginning of your slides, you mentioned you're saying point of contraflexion, right?
Yeah.
What does it mean m equal to 0? What loads are you applying?
So at the point where m is equals to 0.
Mhm. Like how is it m is equal to 0? Because you're having multiple kinds of loads. You're having dead load, live load, wind load, like lot of loads, mainly dead load and live load, let's say.
Uh-huh.
How are you getting your m equal to 0? Is it due to just the dead load only or combination of dead load and live load together?
The first one is the combination. The first one is the positive, like the positive factored moment, and the second one is the negative factored moment. Like we calculated for throughout the span, like the span was around 337 feet in length. So like the sections where it was, like we can say, like throughout the section where the moment, how the moment is moving.
Yeah, how it is changing, that
Yeah,
is
how it's,
correct.
yeah.
But Ahmed, can you confirm the orange is the full load and blue might be
So
just the
no,
dead
so
load
what
probably?
it is, both of
Yeah,
them are like dead plus live.
both
So
are
for
dead
live
plus.
we have like envelopes, right? Like the max
Oh,
positive
Mm,
and
okay.
negative. Yeah.
regular,
So the
yeah.
orange one is like the maximum for maximum live load. The
Mm-hmm.
blue one is for the minimum live load. So deck is
Okay.
also dead load is also included in this. So
Okay.
this is dead plus live.
Okay. So this m equal to 0 is for both. And how do you decide where you want to put your splice?
So, like we decide, like the first one is the positive factor moment, and the second one is the negative factor moment. So we see like what like how big the sections can go on to be. Like
Mm-hmm.
we cannot put a longer section. So if we have a smaller section, like smaller, like as per Ahmed said me, like you do not go beyond 90 feet. So the
Mm-hmm.
first, so we were actually trying to put three splices over here. The first one was between here, like 50 and 60, and one was here between 120 to 130, like somewhere around 125, and the third one was around 247, I guess. So, yeah, these are the 3 points we were trying to put these splice plates.
Yeah, in fact, like splices, generally we do not put at the support locations
Hmm.
Yeah.
and at the maximum moment location. In the
Yeah,
middle
in the middle.
or at the support location, we do not put. So we
Uh-huh.
put somewhere in the middle of the span and end of the support. And
Uh-huh.
there, I think where moment is smaller.
Hmm.
So a net moment or envelope of the moment is smaller.
Hmm.
So there you should put. So that is, I think,
Yeah,
my
that
opinion. And
no,
Yeah.
that is correct. Wherever you're attaining your zero moment, almost
yeah,
your envelope
almost.
is becoming zero or close to zero is
Hmm.
your location. That's the range that it gives.
Hmm.
And the number of or the actual length of the member is decided by the practical limits of the trucking and everything, like for the transportation.
Hmm.
Yeah, you can go up to like 140 feet if it's a plate girder, like a built-up
Hmm.
section,
Hmm.
meaning they can build a 140-foot length of an entire girder segment in a single as a single piece,
Hmm.
load it up onto a truck and deliver it to the site. If
Hmm.
it's a rolled section, it gets tougher to do that big of a length because you would fail with its own dead weight if the piece is not picked up well.
Okay.
So the rolled, the practical application in general, we go around 100, 110, not more than that. For the plate
Okay.
girders, you go up to 140.
Hmm.
Obviously, you look at your span considerations. If your span is like 200 feet, you
Hmm.
definitely need a splice. So you would put a splice around like 120, depending again where your mid span is, where
Hmm.
your middle support is.
Hmm.
Obviously, like Mansur said, you would not put your splice at the mid of the span or at the support. So you
Hmm.
would try to see it would come out around like one third, one quarter of a span in the second span or a first span.
Hmm.
and you put your splice location, you assign your splice location there.
Okay.
Other thing to note is that splices can be two types, like in terms of the construction. It can be shop splices, it can
Mm-hmm.
be a field
Fields.
splice.
Field splice.
Shop splices is something that they do everything, like the plates welded or bolted
Mm-hmm.
in the shop.
Mm-hmm.
And field splice is something they would do this splicing in the field.
Mm-hmm.
And you could also do the splicing without bolts as well. They would do a welding as well,
Welding.
welded splice. But it's mostly shop, and it is very rare that we see such kind of things in the transportation, or at least in the roadway bridges for
Okay.
us.
Okay.
Good.
Yeah, that's all from me. Anyone else? Any questions? But yeah, good presentation. I
Yeah.
think this gives a comprehensive idea on what the spreadsheet is, what calculations there are, and all of those things.
Yeah. Thank you.
Very good.
Yeah, I think NYSDOT, it is like referring to dead load contraflexure.